When calculating feeder conductor sizes for multiple motors, it's important to understand how to apply the 1.25 multiplier. According to the National Electrical Code, specifically in the context of the 2002 edition, when sizing feeder conductors and protection for multiple motors, you only multiply the full load current, or FLC, of the largest motor by a factor of 1.25. You then add the full load currents of all the other smaller motors at their full rated values. The reason for this approach is to ensure that the feeder conductors and the overcurrent protection devices are adequately sized to handle a scenario where the largest motor is operating at its full load, while all the other smaller motors are also running. This provides a safety margin to protect the conductors and equipment from potential overloads. Let's look at an example. Suppose you have one 10 horsepower 208 volts 3-phase motor and three 1 horsepower 120 volts single-phase motors. First, determine the full load current for each of these motors using the appropriate tables in Article 430 of the National Electrical Code. For the 10 horsepower 208 volts 3-phase motor, let's assume the full load current is 30.8 amps based on table 430.150. For the 1 horsepower 120 volts single-phase motors, let's assume the full load current for each is 16 amps, based on table 430.148. Now, to calculate the feeder conductor size, you would take the full load current of the largest motor, which is 30.8 amps, and multiply it by 1.25. This gives you 30.8 amps times 1.25 equals 38.5 amps. Then, you add the full load currents of all the other motors. In this case, you have three 1 horsepower motors, each with a full load current of 16 amps. So, you add 16 amps plus 16 amps plus 16 amps, which equals 48 amps. Finally, add the result from the largest motor calculation, 38.5 amps, to the total full load current of the smaller motors, 48 amps. So 38.5 amps plus 48 amps equals 86.5 amps. This means the feeder conductor should be sized to carry at least 86.5 amps. You would then refer to table 310.16 in the National Electrical Code to determine the appropriate conductor size based on the ampacity requirements and the insulation type of the conductor. Now let's consider the feeder overcurrent protection. The process is slightly different, but follows a similar principle. For feeder protection, you first need to determine the branch circuit protection requirements for each individual motor. To do this, you multiply the full load current of each motor by a factor determined from table 430.52 in the National Electrical Code, which depends on the type of motor and the type of overcurrent protection device being used, such as an inverse timed circuit breaker or a fuse. For example, let's say that for the 10 horsepower motor, the overcurrent protection device is sized at 125% of the full load current according to table 430.52. So, you multiply 30.8 amps by 1.25, which equals 38.5 amps. This is the branch circuit protection size for the largest motor. However, if table 430.52 permits a higher value, you use that instead. Let's assume that after looking at table 430.52, we determine that the maximum overcurrent protection for the 10 horsepower motor is 41 amps. Now, for the three 1 horsepower motors, you also need to determine their individual branch circuit protection sizes. Let's assume that for each 1 horsepower motor, the branch circuit protection is sized at 250% of the full load current according to table 430.52. So, you multiply 16 amps by 2.50, which equals 40 amps for each of the 1 horsepower motors. However, you would typically use a standard size overcurrent device, such as a 40 amp circuit breaker or fuse. To determine the feeder overcurrent protection size, you take the largest branch circuit protection size, which in this case is 41 amps for the 10 horsepower motor, and then you add the full load currents of the other motors. So, you have 41 amps plus 16 amps plus 16 amps plus 16 amps, which equals 89 amps. This means the feeder overcurrent protection device should be sized at or below 89 amps. However, you would typically use the next standard size overcurrent device. It's important to verify that this overcurrent protection size does not exceed the ampacity of the feeder conductors you selected earlier. If it does, you must increase the size of the feeder conductors accordingly. The key difference to remember is that for feeder conductor sizing, you use the full load current of the largest motor multiplied by 1.25, and then add the full load currents of the other motors. For feeder overcurrent protection, you use the largest branch circuit protection size for any of the motors, and then you add the full load currents of the other motors. Multiplying only the largest motor by 1.25 when sizing the feeder conductors ensures that the conductors are adequately sized for the worst case scenario, where the largest motor is running at full load and all the smaller motors are also running. This approach provides the necessary safety margin to protect the feeder conductors and equipment from overload. Keep in mind that the specific requirements and tables in the National Electrical Code may change with different editions, so always refer to the latest version of the code for the most accurate and up-to-date information. Additionally, it's always recommended to consult with a qualified electrical engineer or inspector for any specific electrical installation or design project. Let's delve into a more detailed explanation of why these calculations are structured in this manner, and further clarify the underlying principles behind them. Firstly, consider the diversity of motor loads. In most industrial or commercial settings, it is statistically improbable that all motors connected to a feeder will simultaneously operate at their full rated load for an extended period. Motors are often used intermittently or at varying load levels, depending on the demands of the equipment they drive. The 1.25 multiplier applied to the largest motor accounts for the likelihood that this motor will be the most consistently loaded and will contribute the most significant continuous current draw on the feeder. Secondly, the National Electrical Code aims to balance safety with practicality. Overly conservative calculations can lead to unnecessarily large and expensive conductors and protective devices, which may not be economically feasible or practical in many applications. The code provides a set of rules that are intended to provide a reasonable level of safety while also allowing for efficient and cost-effective electrical system design. Thirdly, motor starting currents are crucial. Motors draw significantly higher current during their starting period compared to their running current. This inrush current can be several times the full load current and can last for a few seconds. The branch circuit protection for each motor is designed to accommodate this inrush current without tripping, while still providing protection against overloads and short circuits. When sizing the feeder overcurrent protection, the code allows you to consider the largest motor's branch circuit protection device rather than its full load current to account for this starting current phenomenon. Fourthly, conductor ampacity and temperature ratings are important considerations. Conductors have a limited ampacity, which is the maximum current they can carry continuously without exceeding their temperature rating. Exceeding the temperature rating of a conductor can damage the insulation and potentially lead to a fire hazard. The feeder conductors must be sized to ensure that their ampacity is sufficient to carry the expected load current, including the contribution from all the motors, with an appropriate safety margin. Fifthly, voltage drop can affect motor performance. Excessive voltage drop in the feeder conductors can reduce the voltage available at the motor terminals, which can negatively impact motor performance such as reduced torque and increased operating temperature. Sizing the feeder conductors adequately helps to minimize voltage drop and ensure that the motors operate within their designed voltage range. To illustrate with a more complex example, imagine a scenario with the following motor loads. 125 horsepower, 480 volts, 3-phase motor with a full load current of 34 amps, 35 horsepower, 208 volts, 3-phase motors with a full load current of 15.2 amps each, and 2 horsepower, 120 volts, single-phase motors with a full load current of 24 amps each. Step 1 involves calculating feeder conductor size. Take the largest motor, 25 horsepower, with a full load current of 34 amps, and multiply it by 1.25, which equals 42.5 amps. Then add the full load currents of all the other motors. 3 5 horsepower motors at 15.2 amps each equals 45.6 amps. Two 2-horsepower motors at 24 amps each equals 48 amps. Total the currents to get 42.5 amps plus 45.6 amps plus 48 amps, which equals 136.1 amps. The feeder conductors must be sized to carry at least 136.1 amps. Step 2 is calculating feeder overcurrent protection. Find the branch circuit protection for each motor using table 430.52. Let's assume the 25 horsepower motor uses an inverse time circuit breaker, and table 430.52 allows for a maximum of 250% of the full load current. 34 amps times 2.50 equals 85 amps. For the 5 horsepower motors, let's assume they also use inverse time circuit breakers, and table 430.52 allows for a maximum of 250% of the full load current. 15.2 amps times 2.50 equals 38 amps. For the 2 horsepower motors, let's assume they use inverse time circuit breakers, and table 430.52 allows for a maximum of 250% of the full load current. 24 amps times 2.50 equals 60 amps. The largest branch circuit protection is 85 amps. Add the full load currents of the other motors to get 85 amps plus 45.6 amps plus 48 amps, which equals 178.6 amps. The feeder overcurrent protection should be sized at or below 178.6 amps using the next standard size overcurrent device. Always verify that the overcurrent protection size does not exceed the ampacity of the feeder conductors. If it does, increase the conductor size accordingly. Remember that the National Electrical Code is a comprehensive document, and these calculations are just a small part of the overall requirements for electrical installations. It is essential to have a thorough understanding of the code and to consult with qualified professionals for any electrical work. Also, remember to account for ambient temperature correction and conductor deadening factors as required by the code when determining the appropriate conductor size. High ambient temperatures or multiple conductors bundled together can reduce the ampacity of the conductors, and these factors must be taken into consideration to ensure the conductors are adequately sized for the intended application. In summary, sizing feeder conductors and overcurrent protection for multiple motors involves applying a 1.25 multiplier to the full load current of the largest motor, adding the full load currents of the other motors, and considering the branch circuit protection requirements for each motor. This approach ensures that the electrical system is safe, reliable, and efficient, and that it complies with the requirements of the National Electrical Code.